Welcome back. In the last video, we proved the theorem right here that rewrites the definition of linearly dependent and independent sets in terms of number of solutions. So let's make our result more precise so that we can use it with confidence. To determine whether a set is linearly independent or not, we consider the homogeneous linear system. A linear combination of v1, vn gives us the zero elements in the variables a1 through an. If the only solution is the trivial solution, then S is linearly independent. If the linear system has infinitely many solutions, then S is linearly dependent. In this last case, any non-zero solution would give us a linear dependence relation for S. So let's define that so we can use it. A linear dependence relation for S is an expression A1 V1 plus A2 V2 blah 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 plus AN VN equals 0, where A1 AN are specific real numbers. So you need to choose them. You can't leave variables, you can't leave parameters. So our specific real numbers, not all zeros. So you can't use the trivial solution to build a dependence relation because you would have that for any set you could possibly come up with. All right, so let's try an example for which x, so which values of x would this set be linearly independent. All right, so we want to consider a1 times 1, 2 minus 1 plus a2 times 2, 5x plus a3 times x3, 2. And we want to know if we can write 0 that way. And so the set, the matrix that we'll consider is something like this. We want this to be linearly independent. And so if we look at independent here, we need to have only one solution. And so that means if I reduce this, we want 1, 0, 0, 0, 1, 0, 0, 0, 1. So this is not what we, so in order to be linearly independent. All right, well, if the matrix here, let's call it A, if A reduces to the identity, well, that's the same thing as A is invertible, or it's the same thing. I mean, we have the entire invertibility theorem. So it's the same thing as the determinant of A is not 0. I think that's the one that's easiest here. So let's compute the determinant of A. Let me put this here just in case I run out of space. All right, so let's compute the determinant of A. That's going to be the determinant of 1, 2x, 2, 5, 3, minus 1, x2. I'm going to just basket weave. So you take the downward, oh, sorry, it's a bit crooked here. A downward one with a positive sign, so I get 10 minus 6 plus 2x squared. And then I take the upward diagonal and I get minus 5x plus 3x plus 8. And so if I look at this in x squared, I just have 2x squared. In x, I end up with 2x here, then 10 minus 6 is 4. 4 minus 8 is minus 4. And so let me factor this. 2 and 1, so 2 times x minus 1, x minus 2, and I want a plus, so here like that. So I want this not to be 0. That way the matrix is invertible and I have a unique solution. So all values of x would work, except for x equals 1, that would make the determinant 0, and x equals minus 2. That would also make the determinant 0. All right, so here's my answer.